All right, so now we're told we have a muon. A muon is an elementary particle. It has a mass. So the mass of the muon is 207 times the mass of an electron. So we can calculate what it is. 207, mass of an electron, we know is 9.11 times 10 to the minus 31 kilograms. And you wouldn't be expected to memorize that. It would be on an equation sheet if you had it on the test. And if you're not on the test, if you're just doing your homework, you can look it up in the book or just ask Mr. Google. All right, so that's the mass of the muon. And we're asked what's the relativistic mass, the momentum, the kinetic energy, and the total energy if it's traveling at almost the speed of light there, right? 0.9995 times the speed of light. So we want to find the relativistic mass, we want to find the momentum, we want to find the kinetic energy, and we want to find the energy. So what are the equations for these? Well, the relativistic mass is gamma times m0 times the rest mass, which we know. The relativistic momentum is gamma times the normal classical momentum. Kinetic energy is gamma minus 1 times m0 c squared, and the total energy is just gamma times m0 c squared. All right, so what is this gamma? Well, gamma is that term that we were using in all the previous equations, 1 over the square root of 1 minus v squared over c squared. And we can put in our number for v to give us what gamma is going to be, and then we can take our gamma and plug it back into all those equations. So 0.9995 c squared over c squared. So again, c's cancel out. I get 1 over the square root of 1 minus 0.9995 squared, and I get 31.6. So now I can take that value for gamma and I can plug it into all these other equations that I had. So I've got 31.6 times m0. m0 was what we calculated earlier, 1.886 times 10 to the minus 28. And that gives me 59.64 times 10 to the minus 28. And it's a mass, so the units are kilograms. All right, so that one was easy. How about momentum? Momentum is going to be equal to gamma times m0. So it's basically the same as what we had up above, times the v. And to get the v this time, now I need to calculate what the speed is in meters per second. Okay, so it's going to be gamma 31.6 times m0 1.886 times 10 to the minus 28 times v, and v, let me do it, I'm going to do it in red down at the bottom. V is equal to 0.9995 times c, so that's 0.9995 times the speed of light, which is 3 times 10 to the 8, and we get 2.9985, so pretty much 3 times 10 to the 8, which is what we'd expect, because we're pretty much multiplying by 1, aren't we? So 0.9995 times 3 times 10 to the 8, and if I do that, I get 1.79 times 10 to the minus 18 kilogram meters per second. If you look at the notes that I wrote up for this problem, it actually says 0.999. I left out the 5 in those notes. All right, so now kinetic energy is gamma minus 1 times m0 c squared. All right, so gamma minus 1 is 31.6 minus 1, which is just going to be 30.6, right? So I get 30.6 times m0, again 1.886 times 10 to the minus 28, times c squared. Well, what's c? C is the speed of light, 3 times 10 to the 8, and I got to square it. So I get 5.19 times 10 to the minus 10 joules, since it's an energy. And for total energy, I'm just going to do gamma 31.6 times m0 times c squared, again 3 times 10 to the 8 squared, and I get 5.36 times 10 to the minus 10 joules. So the total energy is slightly bigger than the kinetic energy. And what's the difference between them? The difference between them is equal to the rest energy. So that's the energy that it has just due to it having a mass. Okay, so the last problem is going to be one with velocity addition. So velocity addition, we know that when we have things traveling at relative speeds, we can never have two numbers add up together to give us greater than or equal to the speed of light. Nothing can travel faster than the speed of light. So what we have is we have a spaceship that's traveling towards the Earth at a speed of 0.90 c. Okay, and then it launches a probe at 0.1 c relative to the spaceship. We want to know what's the speed of the probe measured on Earth if the probe is fired towards the Earth or if it's fired away from the Earth. So let me draw a little picture. All right, so here's the Earth, and here's my spaceship. It's traveling towards the Earth at 0.90 times c. Let's call it VS for V spaceship. And then it launches another little probe at a speed of 0.1 c relative to it. I don't know, let's call this VP, V for the probe. So it can launch it forward or it can launch it backwards. We want to know what's the sum of the velocities that somebody standing on the planet would measure, right? So if it's moving towards it, classically we'd say, well, it would be 0.9 plus 0.1, or it would be 1 times the speed of light. But we know that anything that has a mass can't travel at the speed of light, otherwise it would have infinite energy, and that's impossible. Okay, so we know that the two must add up to be different. So what's our equation? Well, our equation is that this total speed is equal to the sum of the two speeds, so the speed of the spaceship plus the speed of the probe. But in the denominator, we have a term that's going to be bigger than 1, so that our sum on the top can never be bigger than the speed of light. Okay, so I'm going to take the speed of the spaceship plus the speed of the probe, and I'm going to divide on the bottom by 1 plus the product of the two speeds divided by c squared. All right, so the speed of the spaceship, we know that's 0.90 c. The speed of the probe is 0.1 c, but it's either moving towards the Earth, in which case we're going to use a plus sign, or it's moving away, in which case we'll use the minus sign. And you could think about that, just sort of rationalize it. If you had someone in a car moving towards you, if they threw something towards you, it would be coming towards you faster. If they threw it away from you, it would be going slower. So we know we would subtract the speeds. All right, so let's do toward. So V that we see on the Earth is equal to 0.90 c plus 0.1 c. So that's going to be equal to 1.0 c on top. And the denominator, we have 1 plus 0.9 c times 0.1 c over c squared. All right, so what does that simplify to? Well, the top adds up to 1.0 times c. The bottom, I've got a c squared there and a c squared there. So the two c's on top, two c's in the bottom cancel out. So I just get 1 plus 0.9 times 0.1. So I get 1.0 c over 1.09, and I get 0.917 c. So 1 over 1.09 is 0.917. So the net speed is going to be less than the speed of light, which we know it has to be. All right, so what if I'm throwing it away? So if it's going away, we know that it should be smaller. And now we're going to put in our V probe as minus 0.1. So everywhere it comes in the numerator and in the denominator, I'm going to put in my minus sign. All right, so again, the C's in that fraction, the denominator, cancel out. So on the top, I've got 0.9 minus 0.1, so I get 0.8 times C. In the bottom, I've got 1 minus 0.9 times 0.1. The c's have gone. So I get 0.8 c over 0.91. And that comes out to a smaller number than I had in part A, 0.879 times the speed of light.